Okay. I'm going to put this magnet on this ramp here. Doggone. Thought it was going to roll down. I mean, to put this round ball on the ramp, it rolls down, right? Why doesn't the magnet roll down? That's a little confusing. Well, can you draw me a free body diagram for the magnet? And can you draw me a free body diagram for the ball? Maybe we can come to some conclusion about why the ball goes down and the magnet doesn't. Could be the same thing. I'm very confused here. Okay. Well, most people can sketch a slope and an object. It's a magnet, so it can look like this. The sketch is okay. We're going to abstract this to a free body diagram where the object here becomes a point at the origin and you have an X and Y coordinate system. We have to know how to orient it. We have to know the directions of the force here. Okay. So what forces are acting on this? Well, at the very least, you have the force of gravity. I'll just call that F. Grav for right now, but it's mg and it's going to be in the vertical direction. Okay. And then you have a normal force, and I think everybody's got the normal force perpendicular to the ramp. So I know you heard something I said last time. I know you actually heard quite a bit, but okay, you got the normal force. I'll just call that F norm. Okay. And then you've got frictional force. Then you've got a force, some of you have a force acting down the incline. So let's talk about that. Is there a separate force acting along the incline? Okay, I continue to ask, if there's a force acting down the incline, what's the source of that force? And, is it the ground? Intuitively that something is making that that something tends to want to cause an object to move on an incline. And then somebody says, well, the X component of the gravitational force. Well, that depends on how you got your X and Y axes oriented. Okay. You don't need X and Y axes to know that the net force is the sum of these three forces. And if there's another force, you got to put that in there also. But the sum of these three forces can't be zero. Can't possibly be zero. Why is that? Well, actually, it can possibly be zero. The way they're drawn here, it can't be zero. Now, in first place, a normal force have to be a little bit longer. But this force, well, actually, the way it's drawn, maybe it could be zero. If you eliminate the frictional force, then the sum of these two forces can't be zero. Okay, so let's back up to that. There's another force here if it's a magnet. But we'll come to that in a minute. So any way to put these vectors together head to tail so the result won't be zero? The only way you put two vectors together to get zeros if they're equal and opposite. Okay, they might be equal in magnitude. Okay, but they're certainly not opposite if the normal force isn't vertical. Okay. So if we do this, gravitational force added to the frictional force, we get a resultant force that isn't zero. The other thing we know is perpendicular to the incline, the velocity doesn't change, does it? Velocity is zero perpendicular to the incline, even if you got a ball from the incline, right? Okay, of course, velocity is zero if you got a magnet hanging on that incline also. Now, one other thing you might want to think about, and I had it, thought I had it a minute ago. Maybe not. Okay, we'll do that today. Okay. So, okay, my whole point is, if you've got zero friction or low friction, then you're going to get a result that has to be along the incline. Why? Because unless the ball moves off of the incline or down through the incline, which it might if it's heavy enough and the incline is tissue paper or something. Okay. Okay. And it turns out that then that this force has to be along the incline. I'll say if there's no motion perpendicular to the incline, because that's the case here. More generally, I'd say no acceleration perpendicular to the incline. Okay. So if this frictional force is too low, that's going to happen. Now, if the frictional force is strong enough, then stay stationary. Okay, put a domino there. Okay, domino doesn't slide. Now, if I make the incline steep enough, domino will slide. Okay, magnet won't. Okay, so if this is a domino, right there is a picture of what you got. Steeper the incline, actually the frictional force decreases as the incline gets steeper, as the normal force decreases. The resultant of the gravitational and normal force will continue to increase until it's greater than the frictional force. Now with the magnet, that doesn't happen. Pretty strong magnet. Okay. So you got another force. So this might be like, maybe if this is a domino. If it's a magnet, then you have a gravitational force. You also have a magnetic force, which is a whole lot bigger than the gravitational force. I'd have to make this vector much longer because I think that, you know, got at least 10 or maybe as much as 30 times gravitational force here. Okay. In the force of the magnetic force. This is a magnetic force. And it is a force of attraction. So it is perpendicular to the incline. And now you have a frictional force. Well, let's first of all go to the normal force. Normal force have to be enough to counterbalance the component of the gravitational force that's perpendicular to the incline. We call that the perpendicular component. Okay. And since you got a big normal force and frictional force is proportional to normal force, you could have a frictional force this big. Be your maximum possible force of friction. Now you do have the component of the gravitational force. It's parallel to the incline, and a component that's perpendicular. In other words, this vector is totally equivalent. The gravitational vector is totally equivalent to the sum of these two vectors. Make sense? If I add this vector and this vector, I get this vector, assuming my projection lines are all perpendicular and so forth. Okay? So I can cross out the gravitational force vector and say I've got, I'm right out of the label for this. Gravitational force perpendicular to the incline. That's here. And here's force of gravity parallel to the incline. Okay. Now, this force of gravity parallel to the incline, well, okay. This normal force has to be big enough to counter this force and this force. Okay. So that looks about right. I take this and add this. It looks like it comes out roughly the same length. This is clearly longer than either of these. It should be as long as both of them together, because all these have to add up to zero, because perpendicular to the incline, you have no acceleration. You don't even have any velocity. Okay, velocity remains zero, perpendicular to the incline. Now, if you multiply the frictional, the magnitude of the normal force by the coefficient of friction, you see the coefficient of friction? It's been mentioned in the text. It's a simple idea. So I'm going to assume we kind of know. Okay. You multiply this by the coefficient of friction, so mu times F. Okay. And if you haven't seen it, you will. I'm pretty sure it's in there. I do apologize. There are reasons that I'm not totally focused on what your assignment is. Okay. I know what the chapter covers and I know what the ideas need to be. So I might be a little because of I'll explain in a minute, but okay. Your force of friction can't be bigger than the coefficient of friction times the normal force. It clearly is not this big, because if it's this big, this thing's going to be going up the incline, isn't it? It'll be accelerating up the incline, because you add all these forces together, the only two forces parallel to the incline are this and this. And this is way bigger than this. We know friction doesn't cause things to climb the incline. Friction doesn't cause things to move. It doesn't cause things to speed up. Okay, it works opposite to the direction of motion. So your force of friction, your actual force of friction, in this case, since the friction could exert this much force due to that magnetic force, it takes quite a bit of force. Like that. Okay. Force of friction is only going to exert this much because that's all it's required to keep it from sliding down the incline. Okay. Up and left. And I want to use the lowercase f friction. actual force of friction is only enough to hold the thing still on the incline. Okay. And I'm going to say that's just enough to balance force of gravity parallel. So since the maximum possible friction is more than required to balance the gravity, the force of friction is just enough to balance the force parallel component of the force of gravity. Okay. When we draw the free body diagram, we're going to want the point to be at the origin. We don't want a horizontal and vertical axis for this mass on the incline, because we naturally break the gravitational force into components parallel and perpendicular to the incline. Okay. The component perpendicular to the incline is balanced by at least some of the normal force. Sometimes it's all of the normal force. Okay. In this case, you have a lot more normal force than just enough to balance gravity, because you've got this extra force of the magnet. Okay, well, bottom line then is we want to align our axes with one of the axes parallel to the incline, because that's the direction in which motion is going to occur. Okay. You don't want to be analyzing the motion on the incline with both an X and a Y component. That's tricky enough when you have a projectile. Okay. In this situation, it would be much trickier than the projectile, it'd be messier. So now we sketch our free body diagram. Now, the force of gravity is not in the Y direction, is it? Force of gravity is vertical. Now, people want to put the force of gravity along the Y axis, which it is if you have a horizontal and vertical coordinate system. Since you're tilting the coordinate system in order to accommodate the idea that you only want to analyze motion in one direction, gravitation force there. Okay. Here's your force of gravity. Here's your motion force of the magnet. Somewhat greater than this, a whole lot. And here's your normal force. I guess I should put my y-axis and beyond the end of normal force. Okay. And then you've got a frictional force. There's a picture you want. Okay. If this angle is theta, and my question is, how big is the friction force? And let's say force of gravity is about 5 newtons. It's mg. I think the mass of the magnet is around 50 grams, which would correspond to half a newton. Okay, so what do you think? Okay, about half the class I have a little trouble with this. The gravitational force, here's your angle theta, right? Well, the angle between the gravitational force and the y-axis is also going to be theta. Okay? Because theta is the angle between horizontal and the incline, right? Okay. Gravitational force is perpendicular to horizontal. So it's going to be perpendicular to the incline, which is this. Okay. Now, I'm not sure why anybody decided that it wasn't important to teach people a little bit of rigorous geometry in high school. Probably because they decided everybody should be taking geometry and should take the same geometry course. There are advantages to that for people that are never going to be engineers, and serious disadvantages for people who are going to be engineers, because that reasoning tends to be pretty mysterious to people when they come into this class. Okay. So I don't know what needs to be done there. It's a balancing act, and I'm not the one that makes that decision. But you really want to understand that statement. That this is perpendicular to horizontal. This makes an angle theta with horizontal. So what's perpendicular to horizontal should make an angle theta with what's perpendicular to this thing at angle theta with horizontal. Okay. And you want to think about that until it becomes clear. Okay, well, anyhow, this tells us, little picture here, that we got the y-axis, and you got gravitation theory, and you got angle theta here, which means that this component and this component are I didn't give myself enough room to write this. This component ought to be F grav negative F grav times the sine of theta. Said it wrong. That's a cosine of theta. And this ought to be F grav times the sine of theta. For the numbers I gave you, you basically got this triangle here with angle theta, and you got F grav on this side. This is going to have magnitude F grav cosine theta. This is going to have magnitude F grav sine theta. Okay. Now, a minute ago, I said if you have a horizontal x-axis and a vector of 37 degrees, the cosine gives you the x component, right? Well, that's not the case here. Because the angle of F grav with the x is not 37 degrees, okay? So you go to this triangle, or you go to the idea that, okay, the angle here is 270 degrees minus theta, and use a sine and cosine of 270 degrees minus 37 degrees, okay? Well, I don't want to belabor that. You can easily find the components of the gravitational force, and that should be the first thing you do. Now that you know the components of the gravitational force, which I can write here. I'm going to cross out the gravitational force and write the components. And this component here will be 0.3 newtons. This would be negative 0.3 newtons. Okay. Matter of fact, we could say it's 3 newtons, 0.3 newtons times your I vector, and negative 0.3 newtons times your J vector. Make sense? Now your trigonometry should at this point be intuitive enough that a lot of that is obvious. But it's not always the case. Even if you had a trigonometry course, I'm not sure how many of these problems you had to do, but it wasn't enough to really take over your brain. Make sure it takes over your brain, at least part of your brain that you use to do these. Okay. Takes over your whole brain. I don't know what we'd end up with. I think it'd be scary. Okay. So again, we start by taking the components. Now, what therefore is your force of friction? Can you reason that out? We've said enough, but you haven't had time for it to sink in if you haven't seen it or thought about it. So we'll see if you can answer or not. If you can't, there's no shame in it. But if you come in next time and you can't, you'll be a little bit ashamed. Remember? Okay, so we got a quick answer there. And the answer I kind of liked was, okay, yeah. And that indicates that these forces are equal and opposite, as we said over here, and we understand why, I hope. Because friction is not going to exert any more force than this, because friction is not going to cause this magnet to start climbing the incline. Okay. It's enough to resist any force, this much force pushing down the incline. It's enough to resist even more force. But if I push hard enough, we reach the limit of friction, and my push would be this big. Okay. And well, you kind of want to understand this intuitively. You want to understand adding vectors head to tail, which is really the convincing way to prove to yourself that this can't result in equilibrium. Okay. Can't result in a total force of 0. All right. What about the ball? What's going on with the ball? Can you draw me the body diagram for the ball? The vectors have at least the appropriate relations of length. Vectors that are bigger than others should look bigger. Right. So here's a ball. And just in case you aren't aware of what happens when I release the ball, there it is. It accelerates down the incline. Naturally, you're aware of that. You've measured that acceleration. Okay, well, here's a picture for a ball. Okay, you got your gravitational force, your normal force, and a frictional force back this way. And let's see if my picture makes any sense, because I know the ball is going to roll down the incline. And what it comes down to is the actual frictional force is a lot smaller than the one I just drew. We could compensate for that by keeping the frictional force there and making the gravitational force much bigger and the normal force much bigger. But this is kind of typical of the diagrams that I've seen, and it works. And it'll allow us to see what happens if the frictional force shrinks. Okay, so we put these 3 vectors together. Okay, so we've got a gravitational force, vertically downward, a normal force, and the gravitational and normal force have to add up to give us a vector in the direction down the incline for reasons we said before, because there's no acceleration perpendicular to the incline. Okay. Frictional force has to be along the same line as the sum of these 2 forces, because the sum of these 2 forces is in the direction along an incline. So that the frictional force be here, and your result be here. So this is the resultant force, which we often use symbolized by R, which is the sum of all the forces. So there it is. Okay, now for a ball, it turns out the friction force is much less than this. Okay. Actually, probably qualify that. Frictional force might well be like that. Okay. What happens as the incline gets steep? Well, let's look at the component picture here. Okay. Okay. If I sketch this, a set of X and Y coordinate axes, my X axis is going to want to be parallel to incline because I don't want to have to analyze the motion in both X and Y directions. The motion's all in the X direction, so I want my X axis. Okay, the gravitational force. I'll use slightly longer vectors here. And the normal force. Frictional force look at least schematically something like this. I replace the gravitational force by the gravitational force in the Y direction, which of course equals graph cosine theta, this angle being theta. The X component I knew I was going to write I there. I was already thinking ahead of how I was going to write J for this one. So I wrote J on this. Okay. And anticipated, but I didn't. I could write it like this. Now, another thing I could write is F graph perpendicular. This is F graph parallel. I wrote that kind of small. I didn't think myself to write it. Before we called it F graph perpendicular and F graph parallel, and I could have done that on this diagram with no X or Y axis. Okay. Matter of fact, and then I could cross out the F graph. Okay, matter of fact, I can do that. This is F graph parallel here. This is F graph perpendicular here. And I cross out F graph. Now I've got these components. Okay, and I can see whether I've drawn it correctly. This ought to be equal and opposite to this, but it isn't quite. Didn't draw this vector long enough, but still ballpark, still gives me something to work with. Okay, down here, I might have drawn them a little better. This ought to be equal and opposite to this. Looks pretty close, but it's still not quite exactly right. If you want to be meticulous about it, draw them as best you can so they are equal, so they end up equal and opposite. Okay, these two. Well, that's kind of it. So now we can say that the net force equals total force plus the y component of F ground plus the x component of F ground plus the force of friction. A little careless with my arrows here. F norm plus F graph y is 0 because of vertical equilibrium, or equilibrium in the y direction. It's the 0 vector. These two add up to 0. Because of equilibrium perpendicular to the axis. These two are non-zero. Okay, the frictional force is in the negative I direction, negative X direction, okay? We could write it this way. So that comes out F graph sine theta minus the frictional force in the I direction. That's just what the picture tells you. The F norm is equal to the component of F graph perpendicular to the incline. Here's your force of friction. Works out. That's not a bunch of formulas that you want to memorize. That is how you want to think through the problem. You want to think through in terms of the picture. You want to think through in terms of the components. And your text will show you the whole thing in a slightly different way. Okay, it comes down to the same thing. The idea is, again, the components perpendicular to the incline have to add up to 0. They have to cancel. Because the ball does not even move relative to the incline. It stays in constant position in the y direction, okay? Does not accelerate, so there's no net force in that direction. I've said that a bunch of times, but it's really important to understand. Okay, a couple other situations. Over here, you see a pendulum. If you got a pendulum and you got a vertical line, you got a string, and you got a ball on it. Can you draw me a free body diagram? I swear I hit the record button when the red recording pause thing was, and it gave me a recording pause. I don't know. Okay. Got to be careful with this thing. Okay, so, well, here's a pendulum. Okay, and you got a thread here that's attached up here. And you got obviously which is just half times the acceleration of gravity, acting negative or acting down. Okay. Now, if it wasn't for the string, this thing would just fall freely under the influence of gravitational force, right? So it'd accelerate downward at about 9.8 meters per second squared. So what else is acting on this thing? Well, there's no magnetic force. We'll assume magnetic forces are all zero. There are no gremlins around. Chased them away this morning. Okay, they'll be back. What's in contact with the ball? Well, the string and the air. Okay, so the string can only exert a force due to tension. Okay, like if I put this magnet at the end of this beam, I can move the magnet back and forth this way, right? Okay. Now the beam will also, I hold it like this, be exerting a tension. It helps hold this magnet, right? There's tension in the beam that in part supports the rest of the beam, but it also supports the magnet. Okay. Now I can't do this with a piece of string. If I put a piece of string and a mass down there and try to wave it back and forth, it ain't gonna work. Okay. We're not going to wave the thing back and forth. So the string can't exert a force perpendicular to itself. It can only exert a force parallel to itself. And that's a tension force. Now, what's a tension force tend to do? And it won't exert a compressive force. You try to compress a string, even if it's a thin string. I mean, it's a big old thick string like this, yeah. But thin string, you can't compress it. It'll just buckle down, whatever. Okay. So it can only exert a force of tension, and the force of tension is such that tension pulls the string, tension inside the string pulls this point of the string in this direction and this direction, pulls it in opposite directions. Okay. Pulls the ends of the string in opposite directions. And since this ball is attached to the end of the string, it's going to pull, the tension is going to pull it this way. There's a tension up here and equal an opposite tension, assuming it's a light string and you can ignore its mass and its weight. Okay. There's a tension here. I'm not going to put an arrow with that. I've got a direction on it. And there's a tension here. Tensions have equal magnitude, so I can call them both T. But once I put the vector on it, this T is going to be in the direction opposite this one, right? So if I do its components and whatever. Okay. Well, I'm not even interested in this one. Really, I'm only interested in this much. This is just incidental to what happens to the ball down here. It's necessary, but we don't have to analyze it. This is all we need to analyze. And then a lot of people put in a drag force. Which you saw in your differential equations course, which might be where you remember it from, and you might have seen it in some of your engineering courses. I don't know. Where did you see it? Did you see it in differential equations? Well, you certainly did. You seen it in an engineering course? It's okay. Nobody will identify from that. By the way, I just pointed your, the people don't know where you are. That's good. Okay. Okay. So have you seen it in any other course other than differential equations? So I'll be able to go tell Jason that you remember something. You will if you've been in his course. Okay. I'm glad he's having fun teaching that course. I taught it. I taught that course more than 100 times. And I love teaching it. The way the schedule works out though, I've got the multivariable, he's got the differential equations for mean future. And he's happy with that. And much as I'd like to alternate between the two, doesn't work for my schedule. Okay. And he'd be happy switching. But since we're both happy with what we got, that's what we got. Okay, well, I'm glad you remember that. Okay, so if we assume that the drag force is negligible, because this thing isn't moving that fast, you know, drag force is proportional to your speed, right? If it's a pendulum just making small oscillations, if the amplitude of motion is small compared to the length, do you know what I mean by the amplitude of motion? I mean, used amplitudes in differential equations, but not in this context. It's just the maximum displacement from your equilibrium position, okay? It's the amplitude. So let's say it's a meter long and an amplitude of 2 centimeters. Move 2 centimeters this way, 2 centimeters that way. Look at what it's doing right now. It's probably moving about 1 centimeter in each direction. Still moving. Indicating there's not much drag. Okay, because drag would suck the energy out of the system to make that more formal later. There's also flexing in the string, and that dissipates energy as well. And when, you know, I haven't tried to compare the effect of drag with the effect of flexing of the string. Depends on the mass. A big mass concentrated in a small area, you wouldn't have any more drag than you would for a smaller mass in the same area. So if your pendulum is dense enough, certainly the flexing of the string would exceed drag force, but that's down the road. We're not even going to try to analyze that. Okay. Okay, so point is, you got this. Now, can these forces possibly be in equilibrium? Well, if you ignore the drag force, no, they can't. Okay. So let's just say, okay, the drag force is so small that we're going to just kind of spare it out. Meaning we regard it as negligible. Can these forces be in equilibrium? Yeah. Thought that might be a signal of an answer. Confusing me anyway. Okay. It's paused and I hit the play button and it says recording stopped. Never seen that before. I said, look at that fixed. Okay. Okay, these, unless you're in unless the string's vertical, these things can't be equal and opposite, so they can't be in equilibrium, right? And clearly, if you put these forces together, you get result here. Force and tension. And the sum of all your forces is here. Now, if this thing is very close to being at the equilibrium position, which would be for a small oscillation. Then the picture looks like this. Got to draw it bigger, you won't be able to see anything. And there's that graph, here's the force of tension. And they're very nearly equal and opposite to the extent that the result is nearly horizontal. Okay. If it's at near equilibrium, it's not written very well. This means that very near horizontal, the acceleration is very near the vertical. The pendulum is very near the vertical. The horizontal, the acceleration is very near the horizontal. And we get this differential equation, turns out. And we'll analyze this probably next time. Net force is negative Kx. Net force of mg. Mg is negative Kx. Acceleration of gravity. Well, the second derivative of your position function, and obey this, and you're going to get x double prime equals negative k over mx, which you can easily solve using techniques of second order differential equations, or just use little common sense, knowing that a derivative of a sine is a negative, the second derivative of a sine is a negative multiple of the sine, which gives you the equation of motion for pendulum, which is totally not uniformly accelerated. Okay. And we'll flesh that out next time.